Well, welcome back, and I hope you and your family are well. So today's lesson is one of the required practicals in the lower sixth, and it's measuring Planck's constant using LEDs. We spoke a little bit about this last time, but never got a chance to do the practical. So you might remember me telling you a little bit of a story about LEDs that I remember having one or two of these when I was much younger. They were really uncommon then, and I really wanted to play with them. So I got a single battery, a single cell, and tried to light up the LED. And I was a bit surprised by the fact that it didn't light up. So plug this green one in and plug it into 1.5 volts, and it doesn't light up at all. And I have got it the right way round. I was clever enough to realise that. And the trouble was I only had those 1.5 volt batteries. But when I got a PP3, that's the 9 volt one, I noticed with a much higher voltage they lit perfectly. And I didn't really know about what I'm going to teach you today. But if you investigate this a little bit further, I think you'll remember that you need a voltage to light an LED, and different colours of LED need different voltages to light them. And about 1.5 volts here is not enough to light the red one, but it'll definitely light with 3 volts. And the green one needs a voltage slightly higher than the red one just to light. So it's that we're going to investigate today. I'm going to try and explain why that's the case. And then we're going to see if we can use different coloured LEDs, different wavelengths of light, to measure Planck's constant. But you might want to stop the video now and have a quick look at my other film, FJ's physics film, on LED colours. Because it's really important you understand for this experiment that the colour of the LED is not due to the plastic case. And in fact, I show completely colourless LEDs in that film, giving off different coloured light. So have a look at that and then come back to this film. So to work out Planck's constant, and I'll explain how we're going to find that out in a minute, we're going to use LEDs of different wavelengths. They give off different wavelengths of light. And I've got a series of LEDs on this rather nice piece of apparatus. And this one is 450 nanometers, so it's a very short wavelength one. And this one is 950 nanometers. So knowing what you know about light, at this end it's going to be a purpley colour, and the long wavelength one is probably going to be in the infrared spectrum. And what you do with this apparatus, if we were to use it at school, is you provide a voltage to this end. You can do this with loose LEDs, of course, but they've made this rather nice piece of kit. You need to measure the voltage that the LED just lights up at. So I'm going to plug in a voltmeter that goes across the LED you've selected. And there's also some sockets here for an ammeter. Grab another lead. The reason for the ammeter is that's going to read 0 until you select a voltage just high enough to light the LED. But what I'll do is I'll short circuit it, and you'll see that that green LED is lit quite nicely. And you can turn down the voltage and it goes off, and turn up the voltage and it comes on. But what we need to find is the threshold voltage, the absolute minimum voltage to light that LED. So they provide you with a tube, and you can put that tube over the LED and look down it, and it's actually much brighter than you think. And then turn down the voltage and turn down the voltage until the LED just is on. I haven't done it quite as well as I could. I've just quickly demoed it, but I've got about 2.1 volts here. But I can guarantee that if I go up in frequency, it has to be this way, of course, in other words, down in wavelength, that we'll need a higher voltage to get the LEDs just lit. So, for your required practical, remember, you've got a range of LEDs with different wavelengths, and you're going to look down a darkened tube to minimise the background light from the lab and see what voltage is needed to just get each LED lit. And then you're going to record those in a table, and then we'll process that data. Okay, so let's see how we can use this apparatus to measure or to work out at least Planck's constant. So I thought I might just quickly draw the circuit. So you remember you need a power supply, and we'll draw it in the form of a potential divider, and it needs to be big enough in voltage, potential difference, to light the highest energy colour of the LEDs. So that's into the sort of purpley end of the spectrum. And so we had a variable resistor. So here's our variable resistor. And then we had an ammeter in the circuit, though I just replaced it with a wire for today. And then we had our LED. So here's our LED. And back to the power supply. And we needed to measure the threshold voltage on this LED. So we had a voltmeter across the LED to measure the voltage needed to get it just lit up. So if you're asked to explain this, or asked to say how you would do the experiment, have a good look at that circuit. I'll just go up to the board here. You can see that if we slide the variable resistor right up to the top, we get the whole potential of the battery. Halfway we get half of it, and down here we get none of it. And I'm being careful to make sure the LED is the right way round, so we will get current flowing through it. So at this stage, do remember you need to pause the video from time to time, because it's a fast lesson that, you know, I'm unable to interact with you and take questions, so I'm just sort of reeling it off as a lecture. So an explanation of why the LEDs need different voltages to light up. And if you look at the table of data you've got in front of you now, you can actually see that, just reaching for it, you can see the 655 nanometer LED needed 1.44 volts, and the 950 nanometer LED seemed to need a much lower voltage, about 0.2 volts. And that's the one that's in the infrared, and we would have used an infrared camera on our mobile phone to see whether it had come on or not. So an explanation of why that is. Now, semiconductor physics and semiconductor junction physics is a bit tricky, and you don't need to know about that. So I'm going to try and show you my sort of easy way of understanding it. Let's firstly look at a red LED. So a red LED, you can imagine the semiconductor junction in the red LED as being a sort of step with the electrons coming along and trying to go down in energy level to give off one photon of light. And the crucial thing is, it's one electron, put it as a little minus there, falling down and giving off one photon of light. So it's a quantum process, it's a one-to-one process. Now, the junction has a particular energy difference in it, and that electron can either be up here or down here, but it can't hover in between. It has to have enough energy to fall down the sort of hill, the potential hill, and if it doesn't have that much energy, it can't flow. Again, it's this sort of quantum, it's either there or it's lower down process. Now you might say, what happens if you turn up the voltage and go further? We're interested in the energy difference to just light. So we need to give an electron just enough energy to go from the high point to the low point and release that as one photon of light, and that photon will have energy equal to HF. So a green LED, same process, but a slightly bigger gap for the electron to fall down. So if you haven't got the voltage turned up a tiny bit more, the electrons won't have enough energy, enough joules per coulomb to do this, so they won't fall. And if the voltage is just enough, they will fall down and release a single photon of light. And that, of course, again will be E equals HF. And I could draw this for blue, etc., but I think you get the idea. So now let's look at the data that we got and see how we can graph that to work out what Planck's constant is. Oh, perhaps at this stage better remind you just very quickly of the characteristic of an LED. I mean, you obviously know this, but it's just gives things a little bit more clarity. So we look at the IV characteristic of an LED, and if you remember, it has, let's do a red one, it has this sort of shape. If it's reverse biased, it doesn't conduct at all, it doesn't conduct forward biased, and then at the threshold voltage, it conducts electricity. And that slope's pretty vertical, in fact, but we usually put a resistor in so the current isn't so large that the thing melts. Now, you can see here that this value there will be just when it conducts electricity. So this value here is the threshold voltage. And shall I add the green one? So green one, reverse bias, nothing, slightly higher threshold voltage, and then up we go. So there's the slightly higher voltage for the green one, and the blue one would be here, and an infrared would be here. So let's now look at how we're going to use our data graphically to work out Planck's constant. I need to remind you of a few little bits of physics here, and then I'm going to explain to you why we use multiple LEDs, because some of you might be thinking, well, why don't we just use the one LED? So we know that the energy given out by a single photon, E, is equal to hf. So that's the single photon given out when one electron falls down. But we also know that the energy given to that electron when it just lights at the threshold voltage will be equal to EV. Now think carefully about what that means. I'm not saying it's a number in electron volts, I'm saying it's a number in joules, but this is the number of joules per coulomb of charge, and if we multiply by the actual charge that was moving, the electron, we'll get the amount of energy on that one electron. So have a think about that one. That's the energy that each electron will have at the threshold voltage when it just lights up. And that will be equal to the energy given out by the photon. Okay, don't get confused with the photoelectric effect and work function and all of that. Okay, we say that this is a 100% efficient process, so the energy given by the power supply to the charge is equal to the energy of the photon that the charge releases when it falls down that slope. Now, at A level, they mess around with F, and if you remember, we were looking at a set of LEDs that had wavelength written on them. So, C equals F lambda. Yep, so F is C over lambda, so we can rewrite this as EV equals HC upon lambda. And most physicists remember that formula because it's used an awful lot. Now, just before we get into the state where we have a bit of a circular argument here, and I can't remember if it was Callum or Jasper who was asking me this, how do we know the wavelengths of the LEDs? Well, that's a very good question. And it's not really fair for me to say you buy them and they come out of the packet and they've got the wavelength written on them, but that's exactly what we do. But of course, you'll be doing some other work, perhaps later on this term, not with me, but with your other teacher, which will show you light passing through slits. And you might remember that if you shine light through slits, you get an interference pattern. And that interference pattern, where the bright and dark fringes are, depends on the wavelength you're looking at. So you can use that experiment with each LED to work out what their wavelength actually is. So you can determine it experimentally. But for A level at this stage, with this experiment as a required practical, they're more than happy for you just to say the LEDs are labelled with their frequency, or luckily in our case, their wavelength. Okay, so let's analyse our data. And this is a little bit fiddly, so follow me through. What we're going to do is we're going to plot a graph of voltage against 1 over wavelength. And I'll justify that in a minute. So this is what our graph's going to look like. So the usual axes. And the y-axis is going to be potential difference, or voltage in volts. And the x-axis is going to be 1 over wavelength. And so be careful, guys, because 1 over wavelength is not going to be in nanometers. Okay, it's 1 over, so it's going to be nanometers to the -1. But We don't work in nanometers, we work in regular meters. So this should be meters to the -1. Now, obviously, you can use nanometers, but you need to correct for that later on when you do your maths. You need to get that factor of 10 to the -9 in whenever you quote nanometers. Now, why are we using axes like this? Well, have a look at the maths we did up here, and let's rearrange for the threshold voltage, because the threshold voltage is something that we actually measured. We knew the wavelengths, and we had to measure the voltage, so that's why it's on that axis. So let's have a look at our equation. EV equals HC upon lambda, therefore V equals HC upon E lambda. Okay, well, let's just push that equation apart a little bit. V equals HC upon E 1 over lambda. Now, if you look carefully at that, you'll notice that H is a constant, C is the speed of light, and that's a constant, E is a constant. So we've got the threshold voltage and we've got the wavelength, and those are the two things that we either looked up or measured. So the skill is to look at this equation and go, oh, look, it's Y equals mx plus c, and the real question is, where is the x? Well, if we make this the x-axis, so there it is, our 1 over lambda, and we make this m the gradient of the graph, there's no plus c, so we don't need to worry about that. What we need to do is plot the values that we got. I'm just guessing where they are. Okay. Draw our line of best fit. And then being really, really careful with units, V and 1 over lambda, okay, we need to work out here the gradient. And you can see from the maths that the gradient of that is going to be HC upon E. Okay, so you know C, yeah, speed of light. You know E, the charge on an electron. So if you get the gradient, you can then work out H, the Planck constant. It's absolute genius. And it's at these moments I get one of those, I know I've said this before many times, but you get one of those spine-chilling moments in physics as a physics teacher. Because just think about what you'd be here if you were with me, what you're doing in the laboratory. What you're doing in the laboratory is you are measuring Planck's constant, one of the smallest numbers you'll ever deal with, just in a school laboratory. Now that's pretty impressive. So, grab yourself a sheet of paper. Okay, don't tell me you haven't got graph paper, just any sheet of paper. Draw the axes, please. Put the numbers on as best you can. Plot the line and see what value you get for H. Now, I'm going to stop for a second to give you some time to sort that out. And then I just finally like to have a quick talk about errors in this experiment. Good, so how did you get on plotting your graph? Now, I hope you remember to put on a line of best fit, and then the one I've never got a good term for, the worst best fit line, so one that could still be reasonable, and obviously there'd be one equally low. And you should do both of those, okay? And then find out the percentage difference between them, okay? And you can then look at what we measured. So we measured the voltage to the nearest, I'm just looking at my data now, 100th of a volt, okay? And the wavelength, should we say we measured the wavelength to within 10%, okay? So 90%, 10% either side of the value it could be, okay? So try and work out what the error was in your gradient, okay? What the error was in our measurements, and then compare it to the textbook value of H. Okay, so there it is. There's Planck's constant with its associated known error at the moment. That's off the internet. I'm not expecting you to go to so many decimal places. Very quickly, let's just talk about why did we ever draw the graph? What was the point of drawing the graph? Well, if you think about it, you can get Planck's constant from one value, from one LED. But what we're trying to do, of course, is when we plot our graph, we'll get points that are a bit high, a bit low, anomalous, a little bit high, a little bit low. And by doing a number of different colours, we can get a line of best fit. And it's the line of best fit we're using to work out Planck's constant, not a specific value. So hopefully it should give us the best value we can in a school laboratory. So visitors have arrived just as I was filming this lesson. Anyway, I hope you made sense of that experiment. Let me know how you got on, and I'll see you next lesson.